Today we will talk on energy balance in coke oven and clean development mechanism. In the previous lecture, you heard about material balance, and material balance is a prime requisite for energy balance. The objective of energy balance is to find the flow of energy. What are the sources through which energy is entering into the, for example, coke oven, and what are the energy outputs. Now, this energy balance, in fact, you can also call it to be energy auditing. You want to audit the energy in terms of its input and output, and the objective is very clear. You want to know what is happening to the input of energy, where it is being utilized, how is it being utilized, where are the energy going to waste, and what can be done. In the present context, the energy auditing has assumed a very important role in all the industries. Now, in relation to energy auditing, let me introduce another term, which is the clean development mechanism. The whole idea is, if you save the energy, you are saving the environment also. That is where the concept of clean development mechanism has been introduced in the last few years, and the clean development mechanism, that is in short it is called CDM, and this clean development mechanism, it allows to develop technologies related to emission reduction, it stimulates sustainable development, and emission reduction. Now, this concept was introduced in order to reduce the emissions which are discharged into the environment by the use of energy of the fossil fuels under the Kyoto Protocol. So, all those technologies which help in reduction of emissions, they come under clean development mechanism, and it has certain its economic benefits. I will not go into the detail. So, now it is in this perspective, let us see how the energy balance in coke oven, it relates to clean development mechanism. So, I will again make the heat balance of the problem which we have taken in the last lecture. We have determined the various inputs and outputs, and I am rewriting those inputs and outputs, because energy balance, it cannot be done without any material balance. So, for that purpose, I am making energy balance for 1000 kg of coal. So, if this is a symbolic representation of coke oven, then here say 1000 kg coal is entering, 1000 kg coal is entering, and it has calorific value 8184 kilocalorie per kg. That is what we have seen. Now, here coke is produced of 724 kg, and its calorific value was 7481 kilocalorie per kg. Then coke oven gas is produced, and coke oven gas was 349 meter cube, or it was 15.58 kg mole, or 153.56 kg, considering specific gravity of coke oven gas, that is equal to 0.44 in relation to air. We have also determined calorific value of this was equal to 113 into 10 to the power 3 kilocalorie per kg mole. That is what we have determined. Now, as a result of this coke oven operation, we have also found that the tar is also produced, and the tar was amounting to 40 kg, contains 8776 kilocalorie per kg as its calorific value. Now, what we are doing is that, say 40% of this coke oven gas say 40% of this coke oven gas, that is 40% of coke oven gas is recycled into the coke oven chamber for combustion, and this 40% correspond to 6.23 kg mole is used for burning and supplying the heat to the coke oven chamber. So, now we are in a position to make the heat balance and analyze the heat balance. So, if we do that, we will consider, say, energy input, or we can call heat input, whichever way you want to understand. So, heat input was calorific value of coal, and that is equal to 8184 into 10 to the power 3. These values are in kilocalories. Now, also coke oven gas because 40% of coke oven gas is burnt. So, accordingly the heat which is entering is 704 into 10 to the power 3 kilocalorie, and that makes a total 8888 into 10 to the power 3 kilocalorie as the heat input. Now, let us see on the heat output side. So, heat output. Now, first of all, calorific value of coke. We are able to get the heat or in the form of caloric value of the coke, that was 5416 into 10 to the power 3 kilocalorie. That was the heat output. Then coke oven gas. The remaining coke oven gas I am talking, because 40% has been recycled and 60% is left over, and I am calculating the calorific value of the 60% of the coke oven gas, which is now discharged into the environment from the coke oven chamber. So, this has a calorific value of 1053 into 10 to the power 3 kilocalorie. Then tar. Tar is also produced, and tar has a 351 into 10 to the power 3 kilocalorie. we are able to recover into the tar. Now, the coke is discharged, for example, at 1200 degrees Celsius. Then coke also carries sensible heat. So, I am calculating sensible heat in coke that is very simple, mCp into delta T, and the Cp value, that is Cp value one can take 0.359, and one can calculate very easily sensible heat in the coke, say through m Cp delta T, where m is say 724 kg, Cp is 0.359 kilocalorie per kg degree Celsius, and to multiply it by 1175, that is delta T, that is equal to 1200 minus 25 by taking 25 degree Celsius as the reference temperature. So, sensible heat in coke, that is equal to 305 into 10 to the power 3 kilocalorie. Then also coke oven gas also discharges at the similar temperature. So, one can also calculate sensible heat in coke oven gas. Sensible heat in coke oven gas. Again mCp delta T, and if one calculates sensible heat in the coke oven gas by taking, for example, Cp as 0.965, and if we calculate the sensible heat in coke oven gas of entire amount of coke oven gas is 349 meter cube, then the sensible heat in coke oven gas correspond to 174 into 10 to the power 3 kilocalorie. Now, of the special attention that I want to draw is on the sensible heat in coke oven, that is the sensible heat in coke and sensible heat in coke oven gas. These are the important things, because rests a calorific value of the coke that you can use it while charging into the blast furnace. Now, here the coke oven gas also possesses calorific value that can be used, and I also would like to draw your attention about the calorific value of coke oven gas. A very large amount of calorific value of the coke oven gas is available. That is what the energy balance suggests you. So, if I want to summarize, say if I want to say what is the energy balance shows. So, energy balance shows the following important thing. That means, first, potential energy of coke or potential energy, that is calorific value in coke, is approximately 66 to 67% of coal. That means, this energy you are able to recover of the original calorific value of coal. Of course, this can be reused for charging into the blast furnace, no problem at all. Second, you have potential energy in coke oven gas. Potential energy in coke oven gas. And this energy also correspond to 21%. It may vary little bit because the composition might vary depending upon the type of coal, carbonization, temperature and so on, but even then a substantial amount of calorific value in coke oven gas is available, and it is of the order of, let us say, 21% in this calculation of the original calorific value of the coal that is a very substantial amount of coke oven gas caloric value is available. Point number. Now here one should also think what you are going to do with the calorific value of the coke oven gas that is available to you. So here itself one should think that this calorific value can be used for, say, in rolling mill, say for furnace reheating, for reheating of slab, bloom in furnaces, because in thermomechanical processing the slab, billet or bloom, they are heated to a high temperature and then they are being rolled. So in that, coke oven gas can be considered its potential application. Another application that one can think of is the steam generation. And the steam can be used for electricity production and whatever the use that you can anticipate for it. Third, a part of the coke oven can be burnt also. Part of the coke oven gas can be burnt in order to create some amount of energy for heating coke oven chamber. So what these all three uses of the coke oven gas will lead to, they will lead to, say, save in energy. Save in energy by partial replacement of the original fuel that were used in all these three units. So that will help, for example, in two ways: the reduction in the fossil fuel as well as reduction in the emissions that were earlier through the uses of fossil fuel. Now, third thing is that you are also observing that a considerable amount of tar is also being produced. So uses of tar. Uses of tar. Tar also, it has a very high calorific value and hence its uses must be considered. When you want to think where the tar can be used of its calorific value, one way is that injection into the blast furnace. Another way you can think of its uses by gasification, as I will show you towards the end of my lecture. Tar can be reused for gasification purposes. Fourth important thing that you observe, that is the sensible heat in coke. A very large amount of sensible heat in the coke is available and hence it must be reused. That means suitable methods are to be devised where sensible heat of coke can be used. Fifth, you are seeing is that, well, heat losses through the wall, though they have not been shown, but if you do the subtraction, heat losses through the walls of the coke oven chamber, not much can be done. What you can do at the most is to have the refractory wall of the coke oven chamber, which is of little bit low thermal conductivity, but then it will create the problem because coke oven chamber is indirectly heated. So not much can be done. About sixth, say sensible heat in tar. Sensible heat in tar and coke oven gas. So this is what the energy balance tells you, the output of the energy as a result of input of energy through the coal. Now here, as regards the potential energy of the coke, we are using it, no problem. Then as regards the potential energy in coke oven gas, we can plan its use in the plant itself, because the coke ovens, they are part of the integrated steel plant. So one has to think its use within the integrated steel plant, and yes, this use can be found out and it can be used. Tar can also be done similar way. Either it can be rerouted for the blast furnace purposes, or it can be used to gasify it and to produce gaseous fuels. Now about the sensible heat of the coke, I have to say something. Now the sensible heat of coke is to be used. Sensible heat in coke, because it has a very large amount of sensible heat, and in the earlier method we used to have wet quenching. For considerable period of time wet quenching was done, and water was vaporized and it is released into the atmosphere. So we require around 0.5 to 0.6 meter cube water per ton of coke is required. Now in using wet quenching, because water vapor is formed, they are lost in the surrounding. So as a result, loss of sensible heat. Loss of sensible heat, point number 1. And second, due to the cooling through water, airborne coke dust, that is as a form of emission, they are also formed, and they are less than 50 gram per ton of coke. So what I mean to say is that this wet quenching, you lose all the sensible heat, and therefore another method has been developed, and that is the dry quenching. In the dry quenching, gas is used to cool the hot coke, and as a result of exchange of heat between the hot coke and the gas gets heated up. So energy is transferred from the hot coke to the gas. So the coke is discharged at lower temperature and gas is heated up, and this heated gas can be used for performing several operations. So now dry quenching, in fact here the sensible heat of coke can be used very effectively. All that you have to develop a system where heat can be stored and then it can be reused. So before I go a little bit about this dry quenching, which is in short is also called CDQ. C stands for coke, D stands for dry, and Q stands for quenching. So before this, I just want to give a feel what amount of coke we are producing in order to sustain the requirement of steel, because for your information, the production of coke is required for the production of steel in all integrated steel plant. Now in terms of that, just to get a feel how much amount of coke is being produced and how much amount of sensible heat would be, so that one is tempted to utilize this sensible heat and at the same time to have a clean environment. Now let us see, for example, coke is the principal fuel which is used in the integrated steel plant. Now most of the plants, they have their captive coke ovens. Now just a figure, say 1 ton hot metal, 1 ton hot metal after losses, oxidation and so on, approximately it gives 0.75 tons of crude steel. Now 1 ton of coal, 1 ton of coal, it can produce 700 kg coke. So in terms of coal requirement, now what I am doing is that I am calculating, if you are producing 1 ton of crude steel, how much amount of coal will be required through coke. So in terms of coal requirement, 1 ton of crude steel would require approximately 1.07 ton of coal, and that is the important. So if you produce a 10,000 tons of crude steel, then you will be requiring of the order of 10,700 tons of coal. Now in an estimation, India would be producing around 200 million tons of steel, 200 million tons of steel by the end of 2020 to sustain 8 to 9% economic growth. About 70% of this 200 million tons will be produced through blast furnace and BOF integrated steel plant route. So that means by 2020 you will be producing around 140 million tons of steel through BF, through blast furnace and basic oxygen furnace route. So in order to produce this much amount of steel, you will be requiring coal of the order of 150 million tons. Also the coking coal, it accounts for 65 to 85% of the primary sources of energy. Now what this calculation means? Knowing the input that India has a shortage of metallurgical grade coking coal, the deficit is met through the imports. So security of metallurgical grade coking coal is important. Security of metallurgical grade coking coal is very, very important. That means one has to find out the means and ways so that coke can be conserved or coking coal, less coking coal is used, and several alternative methods are being developed. For example, smelting reduction, DRI route, development of pulverized coal injection in blast furnace and so on. So this heat balance, it gives you all these informations. Now coming back to the sensible heat, because you see that an enormous amount of coke would be required and enormous amount of sensible heat will be available. So the dry quenching is being introduced as a technology and which is being considered as a clean development mechanism, because first it eliminates emissions which are caused due to wet quenching, and second the coke dry quenching allows to adopt concept of capturing heat and then reuse, that is by cogeneration. I will tell you just little bit in detail. So what is the principle of dry quenching? Principle of dry quenching is that the heated coke is taken in a chamber where gas is passed, the gas is heated up, then it is taken into the boiler, water gets heated up, and the cooled gas is further recycled into the reaction chamber. So, in order to apply this concept and develop a technology, what technology needs, the first thing is that we need to design a reactor, we need to design the boiler, and also we have to see the cleaning of the coke oven gas, because it may contain dust particle and so on and so forth. So, the technology for development of dry quenching, it consists of, for example, first it should have provision to capture sensible heat. That is, you have to design a reactor where coke and gas can be filled up and heat exchange can occur. A counter current mechanism would be very useful, because counter current mechanism ensures a faster rate of heat transfer. And second, you also require to see the use of captured heat, because you are capturing heat in the gas. So, use of captured heat for say steam generation, for example, if we are planning to do that. So, if we see that these are the technological requirements, so this is what the sketch which I have drawn is shows the principle of dry quenching or the technology of dry quenching. Technology of dry quenching. Now, here coke is being placed over here, say for example, temperature could be 1050 or up to 1200 degrees Celsius. Then this is the pre-chamber, and this is the cooling chamber, and this is the ejector for coke. Ejector for coke, say if it enters around 1050 or 1200, it exits at around 200 degrees Celsius. You can think of the sensible heat which you will be recovering per ton of coke cooling from 1050 to 200, that is the heat which is given and the heat which is taken by the gas. So, this is the primary dust catcher, that is here the gas flows, the dust is being eliminated, and this is the boiler. And the job of the boiler is to convert water into steam, and as a result we get steam, rather superheated steam we get, superheated steam at around 440 degrees Celsius. This is in fact high temperature and high pressure steam. Now, this steam which is produced here, it can be used either in the power plants or in the steel works or in the chemical plant, depend upon the location and so on, so many factors. Now, then the cooled gas is at around 170 degrees Celsius gas is discharged from the boiler and it is taken over here. This is the secondary dust catcher. This is the secondary dust catcher. This is the circulating fan. This is the gas circulating fan, and then the gas enters again. The gas enters again at around 130 degrees Celsius. So that is in principle how the dry quenching is done in the practice. Now here say the consumption of gas, the composition of circulating gas is also important because the gas should have high thermal conductivity. So the composition of circulating gas, the composition of circulating gas say is, for example, CO2 10 to 15%, CO 8 to 10%, then hydrogen it is 2 to 3%, and nitrogen is 70 to 75%. So that is the composition of the circulating gas that is being used. Now some say operating data, just to give you a feel. Some operating data of coke dry quenching. For example, in some location the capacity is 56 ton per hour, coke temperature 1000 to 1050 degrees Celsius, coke output temperature 200 degrees Celsius, gas outlet temperature that is the heated temperature is 800 to 850 degrees Celsius, whereas gas inlet temperature is 130 degrees Celsius. Steam generation is 25 ton per hour. You can imagine the size of the boiler and what you can do with the recovered sensible heat from the coke, and that is an important thing. So steam pressure, it is a very high pressure, is around 40 kg force per centimeter square. The steam temperature is say 440 degrees Celsius, and the total gas volume is of the order of 84,000 normal meter cube per hour. And through this method, that is when you charge coke at 1050 and discharge it at 200 degrees Celsius, the heat which is coming in question, considering 56 tons per hour, the heat which is coming in question is around 80 megacalorie per hour heat is being captured in this particular example. You can imagine a very large amount of heat is being captured and is being used. Some of the benefits of CDQ. Benefits of CDQ, that is the coke dry quenching. One is the energy conservation. energy conservation, it is claimed of the order of 0.8 to 1.2 gigajoule per ton of coke. Second, a reduction in environment emissions, a reduction in emissions. Third advantage, better coke quality. Fourth advantage, marginal moisture content, because you are doing now dry quenching, so there is very little moisture is present, and less moisture, it saves coke while charging in the blast furnace. Fifth is the water conservation. So in fact, the technology of coke dry quenching as introduced into the coke oven plant, it contributes to reduction mechanism as envisaged in the concept of clean development mechanism. Therefore, the coke dry quenching is considered to be a technology which helps reduction in emission, and hence it is termed under the class of clean development mechanism as promoted by the Kyoto Protocol. Now, say a sustained considerable amount of developments has also been done for coke oven, for example, tall coke oven batteries they are used, and so on. These are all the developments in case of say coke oven. Now, another thing that you should also see about the coke oven gas, because in the coke oven gas, it contains hydrogen, it contains methane, it contains benzene, it contains ammonia, and so on. As you see all its composition, there are several uses can also one can think of the coke oven gas which is being discharged from the coke oven plant. Now, one use, of course, we take coke oven gas for heating purposes, but there are several alternative utilization possibilities exist. For example, say I will just put say utilization of coke oven gas as a fuel is already a possibility over there, but there could be several other possibilities that one can explore in order to use the coke oven gas. So let me list down say alternative utilization possibility of coke oven gas. Say 1, hydrogen recovery. (56% hydrogen is present). You can think of hydrogen recovery. Another, methanol synthesis. Methanol synthesis. Third, steam generation. For electric power. Fourth, coke oven gas is hydrogen, methane. One can think of use as reducing agent in BF. One can also think of the use of coke oven gas for the production of directly reduced iron. So these are the other possibilities of using this coke oven gas. Now, in order to show these possibilities, let me draw a sketch for you so that you can understand. Now, for example, we have the coke oven battery. Say this is the coke oven battery. The coke is being produced. The coke, and of course it is used in the blast furnace. So here this is the blast furnace, and here the use of coke. Now we have here blast furnace gas. Low calorific value. Blast furnace gas has a very, very low calorific value. Now coke oven battery, you have the raw gas. Raw gas means it is uncleaned, it contains dust particle, and it contains many other impurities. So it is subjected to gas treatment. Gas treatment. Then we can extract tar, and tar can be subjected to the so called gasification. And the gasification, you can produce another fuel, gaseous fuel, because tar contains carbon, hydrogen. So one can gasify it, carbon convert to CO, one can gasify in presence of steam. So further CO and hydrogen can be produced. Now then this gasification from here, for the clean gas, one can take directly here, and from the gasification gas, and this, and from here this. So now it can be used for several purposes. For example, electric power. Electric power one can use. One can generate electric power. Now remember, if from this you are generating electric power, then earlier when you are using fossil fuel for generation of electric power, now you are saving the fossil fuel. Now if you are saving the fossil fuel, you are contributing to the environment also, because less emissions which were occurring through the use of fossil fuel will not be there now because of this particular mechanism of partial production of electricity by the use of coke oven gas. So that is what is important. Second, one can also use to produce heat, because coke oven gas, it is a very high calorific value gas. So it can be used for heating purposes. Many times there is a rolling mill in the integrated steel plant. So coke oven gas can be directed over there for heating. At least partially it can replace, for example, fuel oil. But the only issue over here that the coke oven gas is produced wherever coke oven plant is there, and most of the coke oven plants, they are in the integrated steel plants. So those use one can think of within the integrated steel plant. Another use you can think, you can extract hydrogen. Now it contains 56% hydrogen, and hydrogen is a potential reducing agent, and hydrogen can also save carbon, because whatever reduction that carbon can do, hydrogen can also do. So if you partially replace hydrogen by carbon by hydrogen, of course you are again contributing to reduction in the emissions, because H2 on reduction it will produce H2O, no emission will be there. Fourth, you can also extract methanol. course methanol can be sold in the market, and then one can also think of connecting or producing directly reduced iron. So, these are say alternative uses of coke oven gas. Now, here say part of the coke oven gas, it can also be mixed with the this is the gas mixer. Here the blast furnace gas is mixed and coke oven gas, both gases are mixed, and a mixture can be used for combustion purposes. So, here a mixture of BF gas plus coke oven gas. So, what I mean, if I these are the say alternative uses of coke oven gas. So, in short, what I wanted to say here is that there is a strong correlation between the energy balance and finding out the ways for energy security and environment sustainability. Energy balance is a very, very powerful tool which can tell you the flow of energy and can identify the potential sources of energy output where one can plan what can be done about the energy which is being obtained in the form of product and byproduct. And typical example which I have given, the use of energy balance as a tool to contribute to energy and environment, and you can see from here that by knowing the various quantities of energy in the output, one can plan the use of energy and one can significantly contribute to the saving of primary energy resources, which is being required, because as you know that the fossil fuel reserves are limited. Use of fossil fuel, it creates lot of environment pollution, and any such things where you can reduce the pollution, that will help the environment, and it is in this connection energy balance is a very, very powerful tool. Thank you.